Okay, I want you to imagine what would happen if you were not accurate figuring out how much, let's say, garbage went into a landfill. You could probably add a few more bags and it wouldn't that necessarily be an issue because that's something that's large and it's not necessarily a big issue. Now imagine if you weren't accurate with as all of the pistons and the small inner workings of a nuclear power plant. Let's say that you were off by your accuracy by, say, 10%. Do you think that that would be a good thing in that category? You'd probably be in a lot of trouble fast, and so would other people. There's times when you need to be incredibly accurate, and as scientists, we try to find out how much accuracy is there with our data. That tells us how much we can rely on it, and so we don't put people at risk, or we don't build things that shouldn't be built in the way that they are by not being accurate enough. So I hope that makes sense. There's lots of units we use for this. They're not standard in what we refer to here in America. We don't use feet. We instead use the metric system and more technically the standard internationally standard version of that, but those are interchangeable. So for volume we use liters. I'm sure you've heard of that before. That's the same thing as a meter cubed. And a side note, you ever heard of somebody on TV saying, hey, push 10 cc's stat, right? So what they're saying is cc's, that's cubic centimeters. A cubic centimeter is a milliliter, which we'll talk about in a little bit. But that's not a standard measurement. Instead, a meter would be the standard measure. A gram or a kilogram would be the mass, and in temperature it could be degrees Celsius or Kelvin. Time is in seconds, not in minutes. Be careful with that. If you are ever using units for minutes, don't use just M, use MIN, because minutes and meters could be easily confused there, okay? Here's something that still kind of blows my mind. When you take a measurement, down here, like, you know that this is sort of a graduated cylinder. That's the meniscus, so you would read the bottom of it, right? That looks like about 2 of whatever it is there, probably 2 milliliters. Well, we actually don't just report that because it's given that you're a human and you can probably reason a little bit. And you can tell the difference between these two markings. So what you should actually report is 1 tens digit more accurate than what you're given as your hashtags here. So if you were given 2.1, 2.2, 2.3, and it came between the 2.1 and the 2.2, you might say it's 2.15. You can go 1 more digit of accuracy there. Okay, so this would be 2.1 or 2.0, whatever you want to list that as. And this is 1.5 because it's between the 1 and 2. So that's another common error that I see sometimes. It's easy to say that's 2.5 because you want to bring it down, but the numbers are going there. So look at where you're between before you report that, okay? Okay, so that leads us to significant figures. When we report our data, we need to report the accuracy in that data, okay? There's a set of rules here. Sometimes they can get confusing. But let's start with the vast majority of cases right now. If you have a number that's not 0, it is significant. Done. If you have a 0 between 2 numbers that are 1 through 9, it is also significant because you can tell that you measured that to that degree, right? So that's going to be there. Here's where it gets a little bit concerning sometimes. See how this says 406.0? By putting that decimal there, you're declaring that this 0 means something. Okay? What you're saying here is I measured that and it really was a 0. So it's after a decimal point and a whole number, or and a non-zero number, 1 through 9. then it counts. Okay. Another way to look at it, just like we did scientific notation last time, this is exactly what you would report in scientific notation. You report the significant figures in scientific notation. So if that's one way to remember how to do that, then great. That would be 4 digits of significant figures. Where it gets more confusing is when not to count the zeros. And you can see that I have notes out here outside of class just to make sure that we didn't get confused there. But if you have a 0 that's before a decimal point and you haven't had a whole number, it's just sitting there right here, like right there, then that is a placeholder. It does not count towards your significant figures because it's just saying, hey, make sure that you know that these numbers are coming after the decimal point. If you see how this is sort of the same type of case, these are still both placeholders, okay? So they've got just zeros before there. You would write this 1.5 times 10 to the negative 2. So there's only 2 significant figures right there. Again, if you have something like this, these guys are seen as placeholders. There's no decimal point there to tell you, hey, I really measured that, and so these are just placeholders. Those are the 2 that count. Okay, before I move on to the next level of difficulty, let's practice that, okay? Okay. I'm going to skip this first one because I think it's the most difficult. Let's just go right here. Here we have 1, 2, 3 significant figures only. See how I can add a whole bunch of zeros before that? Those are just placeholders. You still only have 3 significant figures here. This and this are the same thing. So there's 3 significant figures right there. What changes over here? Well, not so much. These are still just placeholders. They're telling you it's going to come after the decimal point. But we haven't gotten to a whole number yet. All 4 of these, on the other hand, are significant. They're coming after the decimal point, and that's also coming after a decimal point and a number that's a non-zero. So it's coming after this, and therefore it is a measured item. Okay, that's how you can tell the difference. Here, all the zeros between these 2 numbers count. So we've got 1, 2, 3, 4, 5, 6, 7. These, on the other hand, do not. I know that because they're just there. What changes between here and here is the addition of that decimal point. Because now that says it's real, so all of these count as significant. And furthermore, if we keep going after that decimal point, all of that would also be significant. Now, when we deal with data, that is either multiplied or divided, we have to look at how much accuracy our data has when we report our final answer. Now before I go there, let's talk about something that's called an exact number. If you count the number of people in a class, that is an exact number. You counted it and there's not like a tenth of a person hanging on the side. At least let's really hope not. Which means that you don't have to worry about the significant figures in an exact number. Conversions are exact numbers. There's a lot of constants that are exact numbers that you don't have to worry about counting them in the significant figures arena. But say this is actual data that you're following. Here I've only got 2 significant figures and here's 4. My answer can't be more accurate than my data, which means that my answer needs to be only in 2 significant figures through either addition or multiplication or division, not addition. So here's what the calculator is going to spew out. Hey, great, fine. Go ahead and do that until the end of the problem, and then figure out what your number should be to actually report. Okay, so your actual answer. Your actual answer needs to be in two significant figures. Since this is a 5, we just do standard round up, round down. 5 would round up, that would just be 1.9. Okay. Now, just be aware that sometimes you have to add in zeros to make sure you have the right significant figures. 1.25 times 4 is 5. Your calculator is going to spit that out. But here I have 3 significant figures, here I have 3 significant figures, and therefore my final answer should also have 3 significant figures. That doesn't seem so bad. Where it gets here, let's do some problems first real quick. Okay. Find my calculator as well. Okay. Let's try these 3 right here. So 5.94 divided by 2.5. The calculator spits out that it's 2.376. But here I've got 2 significant figures and here I've got 3. So I should report my final answer in 2 significant figures only. So my answer would be 2.4 because that rounds up. Oh, this one is hard to take. I'm sorry, but it is. Here's 3 significant figures, but this is only 1 significant figure. We can't be very accurate with this data at all. And 200 times 194 gives me this huge, 8800. But we have to report it to 1 significant figure only. So we've got to actually report 40,000. See how that would round up in one number, because you round this guy up and that goes to 4. Okay. And then finally 0.00565 times 12 is 0.0678. Do the math first, pump it out of your calculator, and then go back and look at sig figs. This has 4 significant figures, but this only has 2. So we have to then report, 0.068, because that has the 2 significant figures right there. Okay, good. I think this seems a little bit more confusing when we do things by addition and subtraction, but it's not meant to be. So when you do addition and subtraction, basically you line up the decimal point. And you can't go beyond the tens place that has the least significant figure. Let me see if I can figure that out a little bit. These go to the thousandths. This only goes to the tenths, right? Well, since this goes to the tenths, I can only report my answer to the tenths. So this might be what your calculator spews out, but you need to round it up to that. So it's actually more of the placeholder in addition and subtraction rather than the number of significant figures. Here's what I mean by that. So here we have 9.132 plus 5. This is the ones, right? So none of this is reported because it's just to the ones. This has 2 significant figures, but that's okay in this case because this actually is still just reported to the ones. Let's do some more examples of that. So 15 plus 1.29564. 15, we're really just going to let this be 16 because that way it's only reported to the ones. Okay. 16 minus 12.56 is 3.44. But what we actually report is simply 3.